the microphone a little bit closer to my iPad. Okay, share the screen. Okay, so everyone see the screen?
Yep.
Thank you.
Yes.
Or yeah, a little bit of the recap of what we covered last week. We talked about Taylor series and how we can use a simple series of Taylor to find approximation for our finite difference method. And we worked only on a few simple schemes of first order forward. So this means that using this simple linear equation, which is nothing than just the slope of your function, using the point of your unknown function in forward, you can really approximate the derivative of your unknown function with respect to any independent variable. So here it's just a derivative to x. And using the same methodology, you can also find a first order approximation using the backward scheme, which is again the same idea, but then using the unknown function in the backward location. And we found that even we can use a second order central scheme, which if you have your unknown function at a given point, which this could be your boundary condition or initial condition, let's say, then using the backward and forward point, you can construct this slope, but here you have actually two time steps. And through this, you can find the derivative of your unknown function, which is really important because if you remember through all these partial differential equations, really the most important part of the partial differential equation is to find the change of your unknown function. And change of unknown function, the meaning is really just the derivative of your unknown function with respect to any independent variable. So it could be change in space or change in time. This is just a change in space with respect to x. And we found that for any approximation through the finite difference method, we need to discretize our system. And discretization should be happen not only in time, but also in space, and space depending on either you have a 1D condition, a 2D or a 3D space of the problem. You could discretize the system in either of these or in all of these for different independent variables. And then we talked about the first type of partial differential equation, or the most simplest one that we're going to cover, which is one-dimensional advection. So we only have the change of my unknown function as time and the change of unknown function in x. So for example, if you imagine that this is the advection or the transfer of a pollution or a concentration of the chemical in a liquid or in a river or a pipe, this unknown function is really the representative of the concentration of your chemicals, right? So let's say you could be in the unit of ppm, like particle per millions, right? Or even you can actually write this in milligram per liter. So how much concentration of your chemical in terms of milligram you have per liter of the liquid, right? So this is really the value of your unknown function. And this is what you are trying to predict what would happen to this value or concentration in time and in a space. This is 1D, so it should be easy to write the equation. Okay, so here in the 1D advection partial differential equation, you only have two derivatives, right? One derivative with respect to t, one derivative with respect to x. So in general, if you discretize this, you should discretize this in a space and only one space because this is x. And then discretize this is in time, which is n on the superscript, right? So everything here in the subscript reserved for space, so you don't have any j and k in this case, it's just I. And then n is really about the time steps. Okay, so we found we can easily write these differential equation with respect to x using Again, the Taylor series first order forward, it's simple, right? The unknown function in the next point at the same time minus the unknown function at the same location, same time divided by the interval where we are taking the derivative with respect to x, so this should be delta x. Also, the change should be with respect to x, right? So time is constant. But when you write these terms, ut, or the change of your concentration or unknown function with respect to t, where of yours your interval is delta t, what is changing is really the time when the space is constant, right? But you are using the next point to find the first derivative of the same point, right? That's why you always have this n plus 1 or I plus 1. You can also write all these ut and ux with respect to the backward method, right? But what we are covering now for this moment, it's just forward. And because we are forwarding in time, so this is FT, forward in time, because this is n plus 1, right? And we are also forwarding on the space, because this is I plus 1. Then we call this FT and FS. And for most of the problems, we actually have this FT because we are trying to predict the behavior of the system in future. Although there are some problems that we are really interested to find or predict our system in the past. But most of the cases we have is forward in time, but then we could actually have the backward in the space or even the central in the space, right? And these are all with talking about these three different methods that we already talked about. Okay, so here what I derive is really FTFS, forward in time, forward in the space. And then what we did was just substituting these two terms into the 1D advection equation, right? And in the 1D advection diffusion, we have this negative c, and as I mentioned here, the c is really stands for the velocity of your field. And let's say if you have a constant velocity that makes your system more simple, then this is just negative of the velocity field in your system times the change in x, and you have this here, the change of t, right? So if I substitute everything in the discretized form into this equation, we derived everything, and we found that the variable that we really are interested to predict is my unknown function in the future, right? That's why you have this n plus 1 here. And if I write everything for this ui n plus 1, this is the final form of the equation for 1D advection in a discretized form that I can use to approximate my ui and n plus 1. Okay, let's see how does this work. I write the equation one more time here so we can go on this equation step by step. This is FDFS on 1D advection. What is the final form? In the partial differential form, this is easy. Just I have this ut is equal to minus v or c. Here I'm just gonna write v. Okay. In any document you can see anything. It could be even delta or alpha or whatever. It doesn't matter. This is just a constant, which is the velocity. Ux, right? This is 1D advection system. So if I discretize this and write everything for ui n plus 1, which is my unknown function at space I next time, which is the future, this is going to be equal to my unknown function at the same point at the current time, right? Minus v, which is velocity, delta t is the time interval, delta x. So this is my time interval. This is space interval, let's say x interval. Then here you're gonna have the unknown function in the next point in the space, right? Again, at the current time minus unknown function current position, current time. Okay, so let's see how does this work in a discretized grid or a grid point, right? So I have some initial condition. It means if I can, let's say this is my 1D system, right? I have only the X, there is no Y, or there is no Z. So I discretize this 1D system in discrete or finite number of points. So let's say this is I1, I2, I3, and so on, right? To I equal to, well, don't write this because it might be confusing, because if I write n, then it will be conflict with the time. So we are just increasing the intervals, right? But this is at time equal to 0. And that's a very special point because this is saying that I have some initial value, right? Or this is initial condition, really. And if this is an initial condition, then all these values should be known, right? There is no problem. All these green points, these are all known. And the problem is not really the prediction of my unknown function at time 0, because you already have this. But then the question is, what would happen to the system through this 1D advection problem for the same grid points, but at time equal to, let's say 1, right? 1 interval, or let's say equal to delta t. And then what would happen to time equal to 2 times delta t, and so on, right? Okay, so if we found that through this equation, what I'm trying to find is really the unknown function at the same point, right, but next time interval. So I'm standing on right on this point. This is the point that I'm interested to find the unknown function. And if you just look into this equation, let's see what we need here, really. Okay, we need UIN, which is this point, the value of unknown function, same grid, but previous time, right? So this is n plus 1, this is n, right? What else? Well, we have some constant. This is just velocity times delta t times delta x. And then here in the bracket, let's see, we need the unknown function at the next point of grid, right? But previous time step, then minus UIN, which is this point. So you're gonna need two values right here, right? The same value but twice, and then one value here, which is UI plus 1 and n. So using these two, let's say if you have just one, the value, you should be able to find this value, right? So using only 2 points, you can predict the unknown function in the next time step. So if you stand on this point and calculate this, then next time we're gonna march onto the next unknown point, right? Now I need to find this point, again using the previous grids. Then I'm gonna move to the next point, I'm gonna calculate this, and so on, right? But then we found that at some special point, there is the last point of my grid, then I need to use these two values. Well, this is good, but what would happen to this point which I don't have any value? And then I think I briefly explained that we can use some sort of trick. We call this point, which is just an imaginary point, or any arbitrary point, and we call this a ghost point. So let's say this ghost, I just gonna draw the ghost, right? And this point, this is just imaginary, And depending on the boundary condition, we can assign some values to these ghost point or imaginary point that would only the purpose or the idea here is just to help us to just put into this equation to find the unknown function, right? Because we don't have the value here. So depending on the type of the boundary condition, the value of u at the ghost point could be different. So let's say the value of unknown function or u at the ghost point depends really on the type of the boundary condition. So we have a lot of different boundary conditions. I'm gonna just define 3 for this moment. Transmissive, that's the most common one of a boundary condition. And transmissive means, all right, let's say if you have a function, let's say a sinusoidal function, right? And your system is 1D. And let's say this is your boundary. So if this function or sinusoidal wave gonna move, right? It can easily just escape from the medium, right? So what you see at the end, if this is your boundary condition, you would see something like this, right? You don't see the rest because it's just escaping from the medium. And that's a transmissive boundary condition. The second type is the solid boundary. So if again, for the same example, if you have a wave, and let's say the wave gonna hit the boundary, right? Then it's gonna be reflected, and you might have actually the merging of different waves of going forward, and then the reflective waves, and this is really having a solid boundary condition. But then the third type of the boundary conditions are periodic, which are very useful for the systems that the dimensions are pretty extreme. So let's say I have a very long physical domain, right? But then this is my wave. And because of the cost limitation, my ability, I don't really like to simulate the entire space. But what I do is just limit my boundary condition to be just like that, right? But then what I do is that I will define that everything that goes beyond this boundary gonna actually go from this side, right? So in this case, I only have defined this space, which gonna give me a lot of advantage in terms of storing, more data in the less dimension, right? So I'm reserving a lot of like memory in my computer just for a limited space. And then let's say if the wave passes through the boundary, right? Like this, then you should be able to see that it's actually coming from the other way to the domain again, right? So this is called the periodic boundary condition. And we're gonna define some of these today. So you're gonna see how this ghost point would work in your system. For a transmissive system, what you can do is that you can actually equalize the ghost value to be equal to the previous value, right? For the initial condition. So this is known, but the ghost point now is also known if this is a transmissive. We're going to see what would happen to the solid and periodic boundary later. Okay, so once you have the ghost point, then you should be fine, right? You can find the unknown function at this point too. And then once you found all the values for this t equal to delta t, then what is next? Moving to the next time interval, right? So once we found everything, then just march on the time again and calculate everything, all the unknown function on all the points. using the same strategy, right? But now you have to use the previous points. These were unknown in the last stage, right? But now these are also known. So these can be turned to the green at this stage, right? And again, you march, and for this point, you need again another ghost point, which is again equal to the ghost point value is equal to the value of the previous point in a space. So this is how you can really march on the space, right? And on the time to find the unknown function or predict or approximate the unknown function for every point in the space and time. Any question?
Yeah.
Okay, go ahead.
Okay, so this thing where we say that our ghost points equal to a last known value, is this particular of just this transmissive boundary condition, or
Yes.
is this an imagination to make the system work, or something like that to make the math work?
Yeah, so
Uh,
yeah, this is just a good assumption for a transmissive system, okay?
so it's an assumption,
Yes,
basically.
just an
Okay,
assumption, right?
okay, it's
Just
not
as
a physical condition.
not really, or
Okay.
it can be also physical if you imagine that this ghost point is pretty close to your boundary condition, right? I mean, if you think about the physics, you have this discrete number which is exactly on the boundary condition, but then we have to limit our domain somehow to have a transmissive system, right? I mean,
Uh-huh.
physically, if you imagine of our famous problem of the 2D pollution in an
Uh-huh.
ocean, right?
Ah.
So our domain is really large, right? But we
Yeah.
are just limiting our domain just to increase our computational ability, right? But
Okay.
then by having some tricks, we are saying, okay, this is transmittive system, right?
Okay, cool. Thank you.
Yeah, sure. For the periodic and solid boundary is a different thing. Any other question?
No.
Okay.
Professor, I'm sorry.
Sure. Yes, go
Uh,
ahead.
this imaginary or ghost point,
Mhm.
uh, like it depends upon us that how many parts we divide, because it's going to be I is equal to uh, whatever number
Mhm.
plus one more to get to the
Exactly.
ghost point.
That is true.
All right, thank you.
And you don't need actually two ghost point on either side, right? Probably one should be enough depending on what type of scheme you're using. So if you're using forward, right, of course you need a boundary condition or let's say a ghost point right here, but it's just one point. So either whether you have thousand of eyes or just five eyes, it doesn't matter. You just need one more ghost point, right? But in on this side. But if you're using the backward scheme, you need to actually use the backward point, right? So in this case, you need a ghost point on this section part or on this side rather than on the right side, right? But it's just one point. Did I answer to your question?
Yes, sir.
Thank you. All right. Any other question? Okay. If not, let's work on this problem. So if you can actually generate or make your simple FDM toolkit in Excel, for this example, you should have learned a lot, and I think you should have a lot of more easy life in the next few lectures. Okay, so this is the example again. Let's use FDFS uh, and build your first FDM code. Yeah, it's also a code, but it's in Excel, right? So on the advection, therefore, this is our equation. Again, I just write negative V. It could be C anything. And it's an advection of a pollution. in a very long river. And I say river because you can actually imagine this in a 1D, right? And because it's very long, then you don't need to calculate the advection in the second dimension, which is y. So if you, or let's say is advection in a pipe or a river, right? So how is this working? Well, you have a pollution in this system which is not really concentrated. It has a distribution of the chemicals. And this is the distribution. In the middle, you have a high concentration. Once you go to the sides, the concentration will be decreased. Let's say you put an ink, right, or a dyed water on a long pipe, then you're gonna wait for a few minutes and you're gonna have a distribution. Okay, the velocity of your system is left to the right. So the river has a velocity, and this is 0.5 meter per second. Okay, what is the distribution? Well, your distribution follows a very simple equation. So your the distribution of the concentration of your chemicals at time zero, and for at the time zero is a function of x. This is your initial condition, right? And you should have the initial condition, of course. And this has a function, a theoretical function. And this is just an assumption. It's the exponential, or e to the power of negative 0.01 times x minus 50 to the power of 2. So I'm not sure if you remember, but actually this is the equation. Do you remember what is this equation for? Or what is the type of the equation? It's actually normal distribution curve. So normal distribution curve if you see the form of the equation, and let me actually give you the dimension of the river so it makes more sense. The length of the river is 100 meter. Okay, now let's look into this equation. If you put 100 as x, then the distribution should be minimized. And once the x is right in the middle, this is going to be 0 because this is a negative value. Your final unknown function will be maximized. And you can actually try this in Excel. Okay, but once you draw the U, or the concentration of the chemical, or your unknown function with respect to x, and just put different, x values from 0 to 100, then you're gonna see that at the middle, this is your distribution. U is going to be equal to, I think it should be equal to 1. Yeah, because it's e to the power of 0, right? This is the maximum point right in the middle. And then you're going to have less concentration and less, and some point it's going to be close to 0. So this is your initial condition. Okay, and what we are interested in is to predict the advection, or the movement of the pollution, right? Using 1D advection equation by having this initial condition and also my boundary condition. So here, my constant here is really the velocity of 0.5 meter per second. So before going into the actual, the writing the code in Excel, just by your engineering judgment, can you tell me what would happen to this distribution using the 1D advection? just by your judgment.
Could you repeat the question?
Okay, I'm
Yeah,
asking
please.
just by your engineering judgment, okay, if you have a distribution like this, and then there is a velocity in this pipe, how is this distribution of the chemicals gonna change in time?
Just gonna move to the right. I mean,
To the right, yes, and anything else?
it's not gonna look like normal distribution anymore. Like
Okay.
gonna be skewed to the, I think it's gonna be skewed to the right, or I don't know how you say that.
So it's gonna be a wider distribution or narrow one.
Mm,
Okay, so it's gonna be moved to the right?
yes.
So
Yeah.
do I have this distribution or this distribution?
Doctor, it depends on Froude number actually. Like the criticality of the flow, whether it's super critical, subcritical.
Okay, this is
Critical
not
flow.
no, this is not super critical, right? That's why the velocity is pretty small.
So it's
So-
subcritical.
Yeah, it's just a Darcy law, right? Darcy's
Yeah.
type of law.
Yeah, then some pollution is able to go against the flux then. If it's subcritical. If it's supercritical, then the entire pollution will move with the flow.
Yeah, again, this is subcritical, right? And there is no diffusion, right? So because there is no diffusion, we can actually assume that this distribution should be almost the same, but it's gonna move to the
Just-
right,
yeah.
right? This this is this is what we can say at this moment because it doesn't involve any diffusion. True?
Yeah, sure.
Yeah, but let's see how does this work, right? Okay, so this was my concentration at this moment. Okay, let's see. Okay, I think you should be ready to work on this on Excel file. You have everything except two other variables. So let's define delta t to be 3 seconds and delta x equal to 10 meter. Okay. And then let's try to simulate for every, as I mentioned, 3 seconds to up to t equal to 15 seconds. Okay, so you need 5 or 6 different time intervals to get to the 15 seconds, right? And the initial condition happens at t equal to 0, right? This is t equal to 0. So let's work on your Excel files. Let's see if we can generate anything to predict this 1D advection using the schemes that I explained. And what is the equation again? This is the final form, right? ui n plus 1 should be equal to ui n minus v delta x over delta t. And this entire thing should be also constant, right? Because velocity is constant, delta x is 10, delta t is 3. So these are constant values. Times ui plus 1 n minus ui n. And this is a final equation. Okay, so I'm gonna give you about 10 minutes. If you have any result before that, let me know. Otherwise, I will start to give you some hint through my desktop in 10 minutes. Okay, and let me know if you have any question. It just has a small hint. What you need to do is really to generate something like this in your Excel file, right? You need to have different cells for different locations and also extend this to the Y direction or the second direction for time.
Doctor, I'm done. Sorry for the interruption.
Okay, great. So can you give me, let me just to double check your numbers. Okay. Let's see. Delta T is 3 seconds. Delta.
I can share my screen, doctor, if you want.
That would be great. Yes, go ahead.
Okay. So yeah, it's just simply started by putting the X values here.
That's great. Okay.
With the top row and the T values in here,
Mm-hmm.
taking into consideration delta T, which is 3 seconds, and delta X, which is 10 meters.
Mm-hmm.
And then I started with U superscript N subscript I by using the equation you gave to us. So e to the power minus 0.01 times the squared difference between 50 and the value of I.
True.
I went ahead at time equals 0. And at time equal 3 seconds, I used the discretization of the advection. I used the value of the velocity in here and delta x divided by delta t, all multiplied by the difference between u at n, I plus 1 and I. And I assumed the ghost point to be equal to the point at 100, which is almost like logical, as it's almost 0 in here. And then I determined it like this, and I applied to the rest of the cells. Here's the distribution is ready for you.
That is great. Okay. This is true. I have one question though. Let's see. The velocity is 0.5 dt.
Sorry.
No, that's correct. That's good. T15. Okay, I'm just trying to double check your numbers, which looks kind of okay.
But I've gotten some negative numbers. I don't know why.
Yeah, of course we would get, and that's something that I need to talk to you or explain what is happening. But then what is a little bit strange is that the concentration is at 50, which is in the middle point, right? It's getting really large to even it's 1 at the beginning, but it's larger than 1 at the second time, which is 2.05. And it may get larger, but this is really large. So can you put your mouse on H4 cell, H4? Okay, so let's see the equation. You use H3 and just click your, okay, good. So using the previous point, then minus 0.5, which is velocity, times 10, which is Vx, divided by 3, which is delta t, times, okay, I3 minus H3. And this is correct, but let's see. The amplification. C5. I see the problem. Okay, so let me share my screen because the very last equation that I wrote has a small mistake. Let me find my Teams. Okay, so the derivation should be this actually. The delta t should be on top, delta x on the bottom. Okay, so that's the correct derivation. But what I just wrote here, this is vice versa. So this is a mistake. So this should be v delta t divided by delta x. So now you can correct this. And once you have this, let's try to draw the concentration of your chemical at different times, at least for time 0 and time 15. And from that, give me some insight on what do you see in the graphs? What can you say, or what type of strange behavior in terms of the values of the concentration you can see from the graphs? And for other students, you have also about another 4 minutes.
I'm ready, doctor.
Go ahead and share your screen.
Sure, here's
Mhm.
at time equals 0, and this is at time equal 9, and this is at time equal 15.
Okay, great. So what do you see? And what is wrong?
What is expected so far? Because the concentration gets lower against the flux and gets almost 0 with the flux, but it's stationary, like the peak is stationary in the middle.
Yeah, so we won't expect that the concentration going to be increased, right? Because we are not
Yeah.
adding anything to the system.
Yeah,
Okay, and then this is also an advection, so you should expect that your peak gonna move to the right, correct?
yeah, it did.
A little bit, yes.
Yeah,
Yeah, on the other hand, you have also some negative values, which doesn't mean anything, especially if you're talking about concentration, right?
yeah,
I mean, the minimum value could be 0, not even not a negative value. So these are
sure.
all the observations through the graphs, right?
Yeah. Yeah, I think this is because we are just taking 15 seconds, but if we will take, for example, 200 seconds, I think the values are going to be different, right? Let's just try it.
Yeah, of course, but then you cannot jump from 15 to 200, right? You have
Yeah.
to
Yeah, right.
you have to discretize the system again.
Mhm. Oh, I reached around 1,800.
Yep. And as your boundary conditions are transmissive, then you should expect that the chemicals going to actually move further from the boundary and gonna escape from the boundary.
Mhm.
And simply, if
170.
if you look into the values, they are basically crazy values at the end, which
Okay.
means which means that your system is not converging.
Yeah, true, because it became negative, like super negative.
It's super negative, and you have super high values, right?
Yeah,
Okay.
both of them.
Which is actually about the nature of this approximation, but I'm gonna talk
Mhm.
about this. Okay,
Mhm.
good. So let me just share my screen from my iPad. Then I'm gonna go to my Excel file. But any other thoughts or questions from students? Okay. Then let me explain just one more slide in my iPad. Okay, this value right over here. This is a very important value in our approximation. So we call this constant. Let me just copy and paste the entire equation for the one-day advection. So this V delta T over delta X is a constant. I mean, depending on what you pick for delta T and delta X and V in the physics, right? And we call this the amplification factor. So depending on all these three values, you would end up with different categories or regimes of the numerical schemes or finite difference method approximation. So for one-day advection, if A, the absolute value for A, is less than 1, then you should expect to see some stable and damping behavior. So what does that mean? In one-day advection, we don't expect any damping in terms of diffusion, right? But this damping is really coming from the approximation, which is kind of an error, right? Because this is 1D. Our engineering judgment is that, or the theoretical really solution for that is that the concentration gonna move with the same concentration, with the same distribution as a function of this velocity, and nothing gonna be changed, right? If this A or this amplification factor is less than 1, this is what would happen to your approximation. The system gonna be stable. Stable means if this is your distribution, you would not get crazy numbers. Your distribution gonna be something less than your initial distribution, but at least it shows some stable condition, right? So it's damping, but the damping is not really a theoretical damping, which is supported by the physics, but this is just an error. And I'm just talking about the 1D advection, right? If we talk about advection diffusion, of course, we're gonna expect some diffusion or damping because of the physics. Okay, if A is exactly equal to 1, then we call this neutrally stable. It means you don't get any damping. You're gonna get exactly a solution like the theoretical value. And if A is larger than 1, then that's the moment that you're gonna get some unstable system, right? So in this case, the initial distribution would actually increase, which is not a stable. So that's the first observation. The second one I'm gonna explain is in the Excel file, but the direction of the velocity is also important. So depending on the direction of the velocity, you would actually need to use a forward scheme or a backward scheme. Okay, so give me just a few seconds so I can have a transition to my desktop. Okay, let's see if I can share my screen. Okay, can you see the screen? My Excel file?
No, doctor.
Not yet? Okay, let's see. Something, share. Okay, what about now?
We can.
Yes. Okay, great.
Yes.
Okay, and yeah, I hope that the cells, I increase the size of the cells. I hope that these are visible enough. Okay, let me see if I can put my equation here so everyone can see. Let's see, maybe I should have it somewhere here. Okay. And the other. Okay, it's not here too. But this is always like what I do when I write the codes in MATLAB or in Excel. I just put the equation in front of me so I won't mess up with the equation really. On the advection, maybe to the advection. Let's see if I have anything here. Okay, I don't have the equation here, but I just write it here. Okay. So my equation is that okay UI. Let's see. Okay, UI in the next time step. This is equal to my unknown function in the same time step plus, okay, I don't know what happens to the equations. Excel doesn't work like the equations in the Microsoft Word. Okay, so this is UI and minus V delta T divided by delta X times UI plus 1 at time step n minus U and I. Okay, so this is the entire equation, and this is my amplification factor. Okay, what I really like to do is that, which is a little bit different from how you wrote the Excel file, is that I just gonna define my input variables right over here. So if I have the input variables, then it's nice because every time you can actually change those variables, right? So I'm gonna just merge these three, call these input variables. And in terms of the input variables, well, you have the velocity or V. Let's put everything in the middle point. In terms of meter per second, so I define this to be 0.5, right? Then I define delta T. This was 3 seconds. Just write the units so that you don't miss with the units too. And then I have delta X in meter. This is 10. And what else? This should be all, right? Do we have anything else?
I'm sorry, can you zoom in just a little bit? Thank you.
Okay, length of your system, this is 100, right? You don't really need to write this because at the end you're gonna discretize the system for the 100, but I'm just writing everything, right? And this is the T, let's say final, which I define is to be 15 seconds. And you can actually calculate your amplification factor, right? Which is okay, the velocity, and you can just write absolute, right? absolute of the velocity times delta t times delta t divided by delta x. So now the amplification factor is 0.15. If you remember, this is less than 1, so we would expect some stable condition, but damping. However, it's not the case because the velocity is positive. So I'm going to talk about this, but let's just try to make this discretization. Okay, so this is what I do. We have the discretization in dx, right? So I have these I, which is the I in terms of the x IDs, right? So I start from 1. These are integers, so we don't start from 0. This is just the ID of the x. And based on this, you can calculate the space, or let's say x in meters, right? So for every ID that you have, you can try to find the x, right? So here you have only 1 delta x, this is 2 delta x, 3 delta x, and so on. For the first one, of course, we are starting from 0. For the second one, well, you have the delta x, right? So delta x plus the previous reference point, and you can go up to okay. Let's see what is wrong. So L. This is my delta x, right? And you know that you can actually fix this value by pressing the F4 of your keyboard. So this is going to be fixed, doesn't change, even if you move for the other cells, right? So the delta x plus the previous time step. So in this case, we are increasing x, and you can go on to the 100, which is my last point of 100 meter of length. And we need actually 11 grid points in terms of the x. Okay, and discretize everything in space. So I would say, let's see how we can write this. If this is the n in terms of this equation, right? N stands for the integer for the time. Or let's say these are the time ID. Now I'm going down, right? To the time space. So this is 1, 2, 3, 4, and so on. For each of these, you can calculate the time, right? So let's say this is the actual time. Or let's say this is the actual time, it doesn't matter. Let's put this as time in terms of the seconds. So these are for x, these are for time. Okay, and you have the delta t, right? So delta t, let's fix this by pushing F4 on the keyboard. Well, the first time interval, the first time is of course 0, but then after that, well, you need to add 1 time interval to the previous time seconds, right? So you can just extend this to be at 15. Okay, now this is really your values, right? The unknown function for any point for any time. So we know that this is x, so I'm gonna just push this one cell further to the right. So time x, right? Okay, so unknown function, we have the initial value, we have the equation. So let's just write the equation. It's just exponent to the negative 0.1, 1, then times your x value, right, minus 50 power 2. So this is my initial condition. And if you extend this, well, you're gonna have your distribution, right? So what I do is just draw the graph for the distribution just to check that everything is working. And I'm gonna just pick these scatter system by the line function. So this is your distribution, right? At the middle, which is 50, you got the high concentration of 1, and then it's going to decrease. Because you have very limited number of points, well, you don't have this nice distribution, right? But if you increase the x intervals, well, you're going to have a nice normal distribution curve. Okay, let's see what would happen for our prediction. So this is really what I'm going to predict through this equation. Okay, right here, this is my ui n plus 1, right? This is going to be the previous point minus the amplification factor, right? Or this entire term. I'm gonna fix this because this is not going to change. The only thing that is changing and moving is really my unknown function. Okay, this multiplied by u and I plus 1. So the next point in the previous time step minus the same point. And this is my unknown prediction of the unknown function for this time, right? I just gonna extend this. However, if you click on the last cell, you're gonna see that, okay, I need another point, which is my ghost points, right? So all these points right here, I just turn these to gray, which are my ghost points. And then I'm gonna turn the value of each ghost point to be equal to the previous cell. So these are my ghost points. Now, the only thing that you need to do is just to extend this second time of prediction to the other cells, right? So now you have a prediction for all the times. Just to check the values, let's just draw another graph for the time at 15 seconds. So my x doesn't change, but my prediction is my unknown function, right? So as you see, my unknown function didn't really even move, if you see. Even after 15 seconds, it's not really moving. It's just amplifying. And because my system is not stable, that would actually happen. Any question? Okay, is this clear? Or let me know if you had any trouble to make this Excel file, which is the simplest case that we are trying to make, right? And if you didn't have a time, I would just encourage you to work on this. If you can grasp the idea, just to understand how we build this simple discretization of 1D advection, you should be really fine for the other discretization in higher space as well. Okay. Let's do a little bit of changing these variables. Okay. So at this moment, the amplification factor is 0.15. I briefly explained that because the velocity is positive, you would not have a stable condition. Okay. So the amplification factor condition that I mentioned, which if it was less than 1 or equal to 1, you have a stable condition, is only one condition. Another condition is really about the direction of the velocity. So just to try this, okay, if I put this as negative 0.5, which means that instead of having a velocity from left to right, you have something from right to left. Let's see what would happen. Okay, so the velocity is now negative. Let's see. Okay, yeah, because my equation is dependent on the amplification. Let's just remove this absolute value, okay? Because the absolute value is just gonna be required for the condition, not for the equations. So if I put the negative 0.5, this is actually my prediction after 15 seconds. And this actually makes sense, right? You have a concentration after 15 seconds, it's going to the left. And it's also, it's a little bit damping, right? The damping here is not really about the physics, but it's really about the amplification factor. And I mentioned that if the amplification factor is going to be equal to 1, then the system is going to be neutrally stable. It means that it's equal to the theoretical value, right? So let's see if we can bring this amplification factor to 1. So what I need to do, okay, this is my amplification factor. Let's just increase the velocity. Okay. I'm just trying different values, right? So if I put this as -5, my amplification is 1.5. So you see a lot of, disturbance in the system. So this is not converging. But then if I decrease delta t to 2, my amplification factor is 1, right? The absolute value. And you see that this is actually the distribution. If I go for the previous times, you can actually see the movement, right? The movement of the distribution is perfectly just moving by 1D advection because I have a transmissive system. It's just passing from the system. There is no damping, there is no instability because my amplification factor is equal to 1. Does this make sense?
Yep.
Okay, pretty nice. Then for the next lecture on Wednesday, let's actually decrease the delta x to be 1, generate another Excel file, and you have to share your Excel file with me. Okay, before the class, just send me your Excel files just by email. I just want to take a look into your Excel file. So the only thing that is changing from the example that I draw on my iPad is that delta x is equal to 1. Everything is the same. And also that if you can generate another Excel file for the case that you have a periodic boundary. I haven't give you the solution, but let's think about this. Let's see if we can generate a periodic Excel file. Then I would like to see that Excel file as well. Okay.
Okay.
Perfect.
Okay, Doctor, I have a question, please.
Sure. Yeah.
So what you said about the amplification factor is that if it's equal to 1, then the like the simulation is gonna be stable, right?
Well, depends on the direction of the velocity. Okay. So if you are using FTFS and velocity is positive, it's not going to be stable. Okay. But if you are using FTBS and the velocity is positive, then it's going to be stable. In other words, the direction of your scheme should be always in opposite of the direction of the velocity. Okay. In that case, if the amplification factor is 1, then you're gonna get an unconditional stable system.
So can I conclude from this that the values of delta t and delta x should be chosen based on the value of the amplification factor?
That is
Like,
correct.
should we?
Yeah, so
should we
velocity is
solve-
just exactly. So velocity is just driven by the physics, right?
Yeah.
You have the velocity, but then you need to first take a look into the direction of the velocity. Based on that, you're gonna pick if you are going to be FDFS or FTBS, okay? And now you can choose delta t and delta x to generate an amplification factor, the absolute amplification factor of 1.
Yeah.
Then
Okay.
your system is unconditionally stable. True.
Great.
Yeah.
Thank you.
Yeah, no problem. Okay, any other question? Okay, and sure, yeah, Maxwell, I will post an announcement with the new parameter, of course. All right, then, have a great night and see you everyone on Wednesday.
Thank you and good
Thank
night.
you, Dr.
Thank you.
Mahmoud.
Bye.
Thank you.
Thank you. Have a good night.
Thank you, Professor.
Thank you.